for the set A, which is defined as the set containing the elements A, B, C, and D, we have to define relations on that set A that have the following properties. Properties as given in A, B, and C. So we'll start with our first one. So in one, we have to define such a relation that is going to be reflexive and transitive but not symmetric. Okay, so let's quickly go through the definition. So how do we check for reflexivity? So here, let's say we have a relation R. So R is defined on that some set A. R is defined on some set A. That means R is, in that case, is going to be reflexive. Set R is going to be reflexive if and only if we have an ordered pair A comma A which belongs to the relation R for all values of A belonging to the set A. So that means we have a set A on which the relation R is defined. We have to pick up each and every element from the set A. And when we pick up that element, if we can form an ordered pair A comma A and that belongs to the relation R, then immediately we can say R is going to be reflexive. Fine. Then we come to the definition for symmetry. So let's say we have an ordered pair A comma B belonging to some relation R. Fine. And then this implies that B comma A belongs to the relation R as well. That in that case we will say R is going to be, this implies that R is symmetric. So it is going to be a symmetric relation defined on that set. That is symmetric. And then finally we say that if A comma B is an ordered pair that belongs to a relation R and we have another ordered pair, and we have to be very careful how we choose that ordered pair. We're going to choose that ordered pair as B comma C belonging to R. So here we are choosing the second ordered pair in such a fashion such that the first element of the second ordered pair, which is B here in our case, this must be exactly the same as the second element of the first ordered pair. Then we can say, and this implies that A comma C belongs to R, and in that case this implies that R is transitive in nature. This is the definition for any relation to be transitive. So here we have defined three definitions. So when is R going to be reflexive, when it is symmetric, and when it is going to be transitive. So using this definition, we'll keep in check of this three definition. We'll try to define relations that are reflexive and transitive but not symmetric, the first relation. So let's say we consider that relation to be denoted by R1. So R1 is going to be a set of ordered pairs. Now here, before taking the ordered pair, what it means that we have a set A containing four elements A, B, C, and D. So if we take the Cartesian product of the set A with itself, it's going to give us how many? It's going to give us a total of 16 ordered pairs, such that we pick up some ordered pairs R1, some ordered pair that belongs to the set R1, such that R1 becomes a subset of this Cartesian product. So we're going to define the set R1. Let's say it contains the elements A comma A. This is one ordered pair. Next we have B comma B. Next we pick up C comma C, and then D comma D, and then we're going to pick up A comma B. Next we're going to pick up B comma C, and then we're going to pick up A comma C. Fine. So these are some of the ordered pairs that we are picking up from the Cartesian product of A and N, and we're saying that each of these ordered pairs belong to the relation R1. So taking the help of this relation, we can clearly say here that R1 is reflexive. R1 is going to be reflexive. Why is it reflexive? Because how many elements are there in the set A? A, B, C, and D. There are four elements. So that means all the ordered pairs A comma A, B comma B, C comma C, and D comma D that are present in R1. This satisfies the definition of reflexivity. So here R1 is going to be reflexive. Fine. Next, let's check for symmetry. Symmetry says that if we pick up any random ordered pair from the relation A comma B, then B comma A must also be present in that relation. So if we pick up, let's say, the first four are fine. So if we pick up A comma A, definitely A comma A is present. But now, if we go to this ordered pair A comma B, here we see that B comma A, that's not present in the relation R1. So this means that R1 cannot be symmetric. So R1 is not symmetric. This is not a symmetric relation. Then coming to transitivity. So transitivity means if we take two ordered pairs, and we have to be very careful how we choose the ordered pairs. That means the second element of the first ordered pair and the first element of the second ordered pair, they must always match. Then we can say that the ordered pair which is formed by the remaining two elements, the first element of the first ordered pair and the second element of the second ordered pair, they must belong to the relation R. Then it becomes transitive. So here we can see that the first four, they are fine. We don't have to worry about the first four ordered pairs. They are going to be transitive anyhow. You can verify that. So if we take A comma A, and then again if we take A comma A, then A comma A is always going to belong to R1. Fine. Now coming to the this ordered pair A comma B and B comma C. So here we can pick up these two ordered pairs because here these two elements are matching. So that means A comma C must be present in the relation R1. Yes, we are seeing that A comma C is definitely present in the relation. So here we can say that R1 is transitive. So here we have chosen R1 to be such that it is reflexive and transitive, but it is not symmetric. So we have defined the relation R1 as given in A. Now next go to the second relation B. So B, let's call it R2. So R2, let's say we're going to consider only two ordered pairs. One is going to be A comma B, and the other ordered pair that's going to be B comma A. So here we're picking up two ordered pairs from this Cartesian product of A with itself. Now here clearly we can see that R2 is not going to be reflexive because the ordered pairs A comma A, B comma B, C comma C, and D comma D, they are not present in the relation. So R2 cannot be reflexive. So R2 is not reflexive. R2 is not reflexive. Fine. Okay, coming to symmetry. Let's check whether if it is symmetric or not. Yes, if we consider the ordered pair A comma B, then B comma A is present. Or we can say if we pick up B comma A ordered pair, then interchanging the elements in the ordered pair gives us A comma B, which is present in the relation. So we have to pick up only one ordered pair in a relation to check for symmetry. So any one ordered pair that we pick up gives us the other ordered pair in with the elements being interchanged. So here we are seeing that R2 is symmetric. So this is a symmetric relation. What about its transitivity? Is it transitive? So let's say this is not going to be transitive because A comma B and B comma A belongs to R2, but A comma A, since A comma A, we'll say that since A comma A does not belongs to the relation R2, although A comma B and B comma A belongs to it, this simply means that R2 is not transitive. It cannot be a transitive relation. So here we have shown that the second relation R2, which we have defined as the set containing the ordered pairs A comma B and B comma A, is going to be symmetric, but it is neither reflexive nor transitive. Okay, and finally we're going to pick up a relation C. So let's define the relation C as R3. We're going to denote it by R3. Let's say this contains the ordered pairs A comma A, B comma B, then we have C comma C, and then we have D comma D, and we're going to consider two more elements, two more ordered pairs. Let's call them A comma B and B comma A. Now as we can see here that A comma A, B comma B, C comma C, D comma D, these are present. So R3, relation R3 is going to be this thing, reflexive. This is a reflexive relation. What about symmetry? Yes, it is symmetric as well because A comma A, its symmetric ordered pair will be A comma A. So this works fine for the ordered pair, first four ordered pair. Now if we come to A comma B, we also have B comma A, or if we pick up B comma A, we automatically get A comma B. So R3 is symmetric. This is a symmetric relation. And what about finally the case for transitivity? So we don't have to worry about the first four. We'll only consider the last two, A comma B and B comma A. So that's giving us A comma A, which is present. It means our relation R3 is transitive as well. So we have picked up a very special type of a relation R3 such that it is going to be reflexive, symmetric, as well as transitive.